I'll go ahead and start there we go. Hello, everyone. I'm pleased to at long last be welcoming everyone back to another installment of the Iowa State Quantum Computing Group Seminar Series. Today's speaker is Wenyang Qian, whom I've personally had the pleasure of knowing for many years now, having gotten our bachelor's degree at Grinnell together, as well as a PhD in nuclear physics here at ISU. Wenyang wrote his thesis on his work solving relativistic bound state systems using non-perturbative Hamiltonian approaches and graduated fall 2020. He recently was chosen for a postdoc position in Spain, Santiago, where he will be joining his wife, Meijan Li, another accomplished nuclear physicist from ISU. Before going, though, Wenyang has kindly agreed to discuss some of his recent work regarding how the traveling salesman problem can be formulated and solved with quantum computers. So without further ado, Wenyang, the floor is yours.
Okay, thank you very much for the introduction. So today's topic is the quantum computing approach to the traveling salesman problem. So here's a brief outline of the talk. In the first part, I'll introduce some background to traveling salesman problem, what I call TSP, and quantum computing. In the second part, we will formulate the TSP as an optimization problem. And in the third part, we will introduce the algorithm today, which is the Quantum Alternating Operator Ansatz, short for QAOA. We'll briefly discuss its workflow and advantages. And we will also discuss several of its key components. And last part, we will introduce our numerical result for traveling salesman using this approach. So we begin with actually a formulation of the traveling salesman problem. So basically, given a list of cities and the distance between each pair of cities, what is the shortest possible route that visits each city exactly once and return to the original city? So that's one of the formulations that you can have for TSP. So pictorially, it's like finding a path that traveling through all the state in the United States like this. So why this problem is interesting? Because for one, it's general cluster problem. Its result can be directly applied to math, physics, biology, economics. So math and physics are probably more apparent. Biology, so recently people have used traveling salesman result to study proton folding. Economics, so you can construct various networks. That would be advantageous. Second, it's an NP hard and NP complete problem based on how your problem is formulated and what kind of result you want to get. So it is of great importance in complexity theory. And lastly, new tools such as machine learning and quantum computing recently, they provide new insight to this very old problem. So a list of available approaches to TSP. So for one, you can have a brute force method to solve TSP. So basically for here you have n cities. So you just need to go through, check every permutation. So you have a complexity of n factorial. And people in 1962, the Bellman, Help, and Karp algorithm is proposed using dynamic programming. So it can greatly reduce the complexity to exponential. And you have several approaches using branch and bound methods. And we have this Grover algorithm in quantum computing. So if you just apply this to a brute force, it will give you a quadratic speed already. Then you have very recently you have this quantum dynamic programming approach, which combines the benefit from dynamic programming and quantum computing and further reducing the symptotics. So these are the back approaches. And on the other side, you also have the approximation algorithm, such as classically, you have this crystal fits algorithm. It's working on a specialized TSP graph, TSP problem. And you will be able to find your optimal solution within certain threshold of the optimal solution. And usually it gives. And today, we will discuss QAOA approach. It's a family of methods that's inspired basically by quantum annealing or originally simulated annealing. And the QAOA name comes from this 2014 very essential paper. It's called Quantum Approximate Optimization Algorithm. And recently it had been rebranded to Quantum Alternating, sorry, it's a typo, Alternating Operator Ansatz by making the method more general. And why we are interested in quantum computing to TSP. So, a few basic features of quantum computing that might be beneficial here. One is that we use a quantum bit or qubit, and the qubit for a two-level system is like this. And the benefits that you can have superposition that is not available in classic computers. So, and secondly, we use quantum gates instead of classical logical gates. So basically, they are unitary operators that you can apply on the circuit. And lastly, the state only collapse when we measure. So in theory, using quantum computing can solve classical problems problems that classic computer cannot solve. So that's a very brief introduction to quantum computing. And the advantages of using quantum computing for TSP is that essentially the state space of the problem, TSP problem, as we will see shortly, it grows exponentially with increasing number of cities. So it's extremely useful to take advantage of quantum computing where we have exponential state space available to us within with n qubits. And secondly, quantum computing approach is very general. So you can expect to apply what you have to a larger problem of optimization, such as vehicle routing, max sec. So all these problems have many things in common, and people have already applied QAOA to almost all of them so far. And lastly, there's a rapid technology progress in performance. You have better qubits, higher volume, higher speed of quantum backends. And so to properly formulate the traveling salesman problem, so we put forth a formulation using graph theory. So given an undirected graph, that is equal to some set of vertices and the set of edges, where the number of vertices is equal to n. Sometimes I also call it nodes. And the edge distance omega ij between vertex I and j. We want to find a size basically that goes through all the nodes exactly once with the smallest total weights of the connecting edges. So as you can see, this is basically how to properly formulate that using graph theory. So here is an example of a 4-city TSP and one of its solutions. So you have the 4 cities labeled with the green node 0, 1, 2, 3, and the edge weight connecting them are listed. And so you want to find what is the best path to go through all of them, which give you the shortest path. So apparently, the solution will be this. So you start with 0, go to 1, go to 2, and go to 3. So that gives you a combined total distance that is a minimum. So to this problem, we put forward some simplifying assumptions. First, what we deal here is symmetric TSP. That means any edge AB is equal to edge BA. So the 37, for example, here is the same whether you go from 1 to 2 or 2 to 1. So there's a bigger category of study where you have TSP, but we'll just focus on symmetric TSP here. So the idea is very similar. It will make the Hamiltonian much easier, as you can see shortly. And secondly, the traveler will return to the initial city, so completing a cycle. Many formulations, they don't have some traveler going back to the original. So the last, so you just go to some final destination, right? And the changes the problem the solution quite a bit. And thirdly, any disconnected edges is represented by a maximum edge weight. Basically, so every edge, every 2 nodes in the graph is connected. So you can think about a disconnected edge like having a very big weight, right? So that's our treatment here. And lastly, the graph is not necessarily planar. So although here you see I put the 4 cities on the plane, in reality they might not satisfy the condition that they can be on a plane, right? So we do not make that as a restriction. So you can think of this as studying the network of traveling salesman problem instead of in the reality. So to mathematically formulate this, we will need decision variables. So a Hamiltonian cycle can be described by a square decision variables, which I call T. So the I represents the node index, and the T represents the time order of that respective node. So for instance, so xit equal 1, and if the node I is visited at time order T. So as you can see in this here, any solution to the TSP can be either represented as a permutation, which I showed in the previous slide, as well as binary decision variables and its matrix form, right? So basically, this tells you that, for example, this case here, this tells you that you visit the 0 city at time equals 0. So that will require you to have x00 being 1, so which is represented here. And you visit the first city at time equals 1, so that here. And when you flatten the matrix, you get this bit string. So this bit string representation is useful on the quantum computer, right? And it can be always translated to a matrix, and the matrix can be translated to a permutation. Although there are definitely a lot of matrices that will not allow you to translate to the permutation, right? So that's an issue that we will worry about. So then they are right. So based on that, we can group the set of all x's into 3 categories, right? So x can be if it's a valid permutation, and also it gives the shortest path of the TSP problem. For example, this permutation is good. So this x for that graph is actually true. Right? So the x could also be false if it is a valid permutation, but it does not give the shortest path. So as you imagine, if you do some other permutation here, like 0, 2, 1, 3, you have a corresponding x. So that x will be false because the distance is not minimal. And you can see majority of the answers will be invalid, that they are not a valid permutation. Right, that's a violation of the TSP because, for example, you have more than once in each row or more than once in each column, then there will be a violation because you're trying to visit the same city at 2 different times, which is not wanted, or you visit the two cities at the same time, right? That's not possible. So it's a violation of TSP. Right. And so now we have decision variables. We can formulate this problem more readily with a cost function. So first, I have to say that we treat it as an optimization problem. And TSP optimization is NP hard. The cost function of a minimization for n cities can be formulated as this. Basically, you try to look at all the sequential binary decision variables, and if both of them lights up, like xit equals 1 and xijt plus 1 equals 1, so that means the 2 nodes I and j are connected as a sequential step in your traveling order, right? And then you take that a weight factor corresponding to those 2 edges, right? And when you sum them up, that will calculate the complete path of your traveling salesman. So we regard that as a cost function. So basically, right. So, and also I forgot to say that we strictly forbidden INJ. So we let omega INJ equal to 0. And any valid decision variables must satisfy the both constraints, as I mentioned in the previous graph.
Wenyang,
Yes.
I just want to be clear. The omega, you said I and J, but you pointed to something omega I is equal to 0. Is that what you said?
Right.
Omega ij in general is non-zero when J not equal I.
Right. So omega ij in general are non-zero, but you want to talk about the edge between two identical nodes, we treat that as 0, right?
Right.
Okay.
Yeah. So just you could put this inside the formulation, but it will make it not as clean. So we put this restriction here. Right. And as I mentioned, because of the conflict, right? So you need to have some constraint on those binary variables. For one, you want xit. When you sum up all the i's, it goes to 0. Goes to 1. Sorry, because this is like looking at a column of the matrix, right? You only want only one of its index is equal to 1. Element is equal to 1, right? And you also want the same thing for the time direction. So you only want to have one valid slot. And but by combining those this cost function, the distance function, and the penalty function, the full cost function to minimize will be the following. And we put a lambda here to control the strength of the penalty. And the penalty is formulated as 1 minus the constraint squared, right? And the one you want to minimize it, there will be guaranteed to be goes to 1, as indicated in the equation above. And usually we pick lambda as the maximum weight, maximum edge weight of the graph. And we see already there's a symmetry in the problem, right? So your TSP solution obtained after the optimization will be physically identical up to some rotation. For example, visiting order of 0, 1, 2 is equivalent to 1, 2, 0 or 2, 0, 1, right? So it doesn't matter where you start the problem. When you finish a complete circle, the path distance is the same, right? So to remove the rotational redundancy, and because basically we want to conserve number of decision variables, a straightforward but very significant improvement can be made by fixing the initial starting city. So without the loss of generality, I fix the city 0 as our starting point. So the simplified full cost function becomes the following. So basically you put a delta function inside the sum, and then this is what you will get. And so in all the results I present in this talk, we will just be focusing on the improved version of the cost function. So the important thing is that the reduction in the number of decision variables. So when you have n-city traveling salesman problem, you used to have n squared number of decision variables, and now you will just have n minus 1 squared decision variables, right? Because you fix the first city. And now we come to the start of today, which is the QAOA approach. So as I mentioned, it has a name change from 2014, 2017, but the workflow is very much the same. So the green box represent what we can prepare or do on classic computer, and the red box is what we do on quantum computer. So as you can see, it's a hybrid approach. So before your optimization starts, you have a graphical representation of TSP. So basically, you want to obtain those adjacency matrices, and then you construct your cost function based on the term that discussed. You have a profit term or a distant term and a penalty term. And you want to map your cost function to the icing Hamiltonian, to a Hamiltonian on the qubit, which I will discuss briefly in the following slides. And after you prepare your problem, so you can start your optimization loop. So on the first, you start on the quantum computer. You initialize your states. So there are several choices here. So in the original QAOA paper in 2014, it's always initialized as a complete superposition. But now you have more variety in how you want to initialize your states. And then you go through a parameterized ansatz, which is of p many layers. And in each of the layer, you have a problem ansatz, which is inspired by the problem Hamiltonian. And you also have a mixing ansatz, right, which helps move your solution around. So with the combination of p such layers, we evolve our initial state. And then we take measurements of the result of that. And the measurement will be a probability distribution of different binary strings, right? The binary strings are basically the decision variables, and the probability are how likely the decision variable is correct. So that's one way to think about it. And then based on those, this histogram or probability graph, you can compute this cost function, right? Just based on, it's based on this, right? You have the binary string, and you can compute the cost function. And you have a number here, and you want that number to be as low as possible. So we use some chosen optimizer to update the parameter for the next batch of iteration. So basically that completes your one cycle of your optimization loop. So in practice, you will do this many times until the classical optimizer deems your parameter is optimal, given the available problem. So this is a basic workflow. And so as I mentioned, it consists of 3 essential parts. And here we just want to formulate it more mathematically. So initialization is very important. It's done on a quantum computer as highlighted in red. The parameter ansatz, so based on evolution of 2 alternating Hamiltonians. So this is your ansatz, U sub p. So it's a parameterized, so it's of 2 parameters. One is beta, one is gamma. Each of length p, which is the length of the number of the layers. So it consists of alternating unitaries. So the first one is the problem unitary operator. So it's made from the problem Hamiltonian, and the second one is the mixer unitary, which is made from the mixer Hamiltonian. So this is a very important, so which I will highlight shortly. And you can see the parameters. So the parameters beta and gamma will go into the phase parameter of each of the unitaries, right? And if you have p many layers, you will need two. So you have p many layers. You will need p many gammas for each layer and p many betas for each layer. So in total, you will have 2 p many parameters, where p is the number of layers. And we also, a last step will be measure the results on the quantum computer, and then subsequently computing the cost function. Right. So why we are using QAOA? What are the advantages? So firstly, it's part of a larger variational quantum algorithm family. So one of the famous one is probably known as called VQE, variational quantum eigensolver. And except the fact that here in QAOA, the unitary ansatz is really Hamiltonian inspired, as opposed to purely heuristic that you would normally see in a VQE. So one can think about this as a problem-driven quantum neural network. That's a very fancy way to put it. And the direct consequence of this Hamiltonian-inspired ansatz is that you have very few parameters. So as I mentioned, you will have only 2p parameters where p is the number of layers. And this does not scale with problem size, right? Even you have more and more qubits, your layer will determine your parameter. So this is very good compared to most of the other variational quantum algorithms. And thirdly, it's a mathematically proven non-trivial performance guarantee, especially on the well-studied max cut problem. And even at p equals 1 layer depth, that you have a guarantee that is good and it's not efficiently simulatable by classic computers. And fourthly, so this is what I found very recently, a few years back. There's a potential inheritance of variational parameters. So your p+1 layer QAOA can depend on your p layer QAOA parameters. So in this way, you can expand your QAOA structure layer by layer, right? So you fix your initial p layers and then you determine only the p+1 layer in this fashion. And there's a big connection to quantum annealing. So that's what I mentioned in the beginning, because partly QAOA is inspired by that. So you can think about QAOA with infinite depths can be viewed as a gate-based quantum annealing approach. And with QAOA here, so one is expected to control or increase the precision arbitrarily by increasing the number of layers, right? So the number of layers is like in a knob that you can control your quantum annealing approach, which is not available before. And lastly, so this is what I found this morning, actually. You can have hardware implementation of QAOA directly using arrays of trapped neutral ions. So this is very recently published in PRX. So this is very promising that people started using quantum system itself to simulate the QAOA now. And so I mentioned the three key ingredients here. So I will just expand them one by one. So the first part is the state preparation. So initial state can play a vital role in reducing the number of quantum states in a quantum simulation. So for a unsteady TSP, so there are several candidates that I have considered in our current results. So first is that the good old-fashioned applying a hard-mark gate to all the qubits. So this will result to a complete superposition of all binary strings or quantum states, right? So it's a complete binary superposition. And if you for an unsteady TSP in the original formulation where you have n squared number of qubits, so this will imply that your initial state space will be of 2 to the n squared. So for a 3-city problem, you have 2 to the 9, which is 512 superposition. So that's a very big state space. So then that's what people primarily use in 2014. And you could also, so this is what I saw recently, you could also apply an array of W state to the initial state. So W state basically, instead of making it a binary superposition, W state will make it a one-hot superposition. So for example, this example here is what you have for each block using W state. So you will have a one-hot encoding superposition of the 3-city. So the advantage of that is you reduce the number of quantum state to n to the n, right? And so and then you within those all the solutions you contain all those valid permutations, right? So you are not losing any solutions. And thirdly, you could formulate this as a superposition of all permutations, right? So the Pn here is the n-order permutation group. So for the 3-city, you could have 0, 1, 2 and 0, 2, 1, all those kind of permutations. and you convert that into binary strings, and you put forth a superposition of them. Right? This is good because this will give you the smallest a set of initial states that contains the valid permutations. But this might not be easily do on quantum computers. And lastly, you could start with just a single permutation, right? So the state space is just one. So you have this tower of reduction of the size of initial states, and they strictly follow this relation. And for the first one, you have a lot of invalid states. For the one hot position, you have much less invalid states. And for the last two, you have strictly valid states. So valid in the way that I defined earlier, which means it's a valid permutation. And examples of the initial state for Swiss cities, so I introduced here already for S2. So for S3, so this is like a valid superposition for Swiss cities. So as you can see, this would be permutation from 1, 2, 3. This will be 1, 1, 3, 2, etc. Okay. And speaking of the ansatz, it consists of the cost Hamiltonian. So the cost Hamiltonian is based on the cost function. So for n-city TSP, the decision variables are encoded or embedded to qubits as the following. So I introduced the decision variable before, right? But it's not on quantum computer, so you will have to encode that in quantum computer. So that is a very common way to do on quantum computer, is by encoding the binary 0, 1 into 1 minus the z gate over 2. The 1 minus the z gate over 2 will have the eigenvalue and the eigenvector aligned with the decision variable x. So that's why people do that. And in the original cost function, you have m squared qubits. But if we use the simplified cost function, which by fixing the first city, you will have only n minus 1 qubits. And so you apply this mapping to the entire cost function, right? So the cost function will be mapped to the Hamiltonian, which consists of the distant Hamiltonian and the penalty Hamiltonian, right? And if you clean up the algebra, in the end, you will have just a superposition of different z-gate and poly-z matrices and poly-z-z matrices. So this is Ising Hamiltonian. And with this Hamiltonian, we will introduce the mixed Hamiltonian. So the goal of a mixed Hamiltonian here is to perturb your quantum state out of the eigenstate of the problem Hamiltonian, because without this term, you would stuck at the problem Hamiltonian once you are already eigenstate, right? So the mixer will help perturb that in search of a local or global minimum. So the mixer for that to happen, the mixer must not commute with the problem Hamiltonian, right? So in general, you have this, and as I showed that the problem Hamiltonian will be entirely of Z and of ZZ poly matrices. So some candidates for the mixer here. So you could have you could apply the X gate on each of the qubits. So basically X rotation on each of the qubit. So that is originally proposed, right, with the QAOA approach. And very recently, you can use this is the so-called XY gate. So the XX plus YY is called a XY gate. You can apply a lot of the XY gates on the qubits. So you have different structure for the XY gates. And speaking of the XY gate, because it's very essential to this problem, so I will just briefly talk about that before we go back to the mixer again. So the XY mixer, so its basic form is of the following. So you are basically applying the poly X and poly Y consecutively on 2 qubits I and J. It has this nice property that it conserves the total probability of the so-called Hamming weight of the 2 acting qubits, which is especially designed in combinatorial problem because sometimes you just want to flip the position of the ones. And it's also very simple on the circuit. So you just have this very simple structure on the circuit. And as you can see, the evolution of the XY gate. So basically, that's what's happening on the circuit. You have parameter theta, is a phase parameter, and your probability is for your measurement as a function of the phase theta is seen here. So you are able to probe all the two-level linear combination of those these two qubit positions, and their total combined probability is always equal to 1. So that's a very nice property. So in the case that if you want to swap two qubits, the content of two qubits without changing the contents of all the other qubits, so that's where the XY will shine. And here, basically, this part is this XY, and I'm applying the XY on the I city and J city for all the corresponding time. So if you try to visualize it, it's like swapping the two rows of your the decision variable matrices, right? And now I need to swap all of the possible rows so that I have the sum here. So basically, that's the idea behind this mixer ansatz. And sometimes I call it RS because it's really a row swap ansatz. So there have been a lot of studies of this ansatz. And you could also just naively group the XY gate as the linear entanglement, right, on the circuit. Right.
So let me ask a question here. The mixer Hamiltonian. Let me suppose that an iterative approach has been going on for a while, and the calculation now accidentally, or maybe you could say because of design, actually hits the exact solution. All right. Now you happen to just land on the exact solution, the best solution. Now your mixer Hamiltonian actually can come in and kick you out again of the exact solution, correct?
Right, that's right. But you can kick you out with the parameters there, right? But your classical optimizers might not like it. So it will revert back to the parameter you had before the iteration.
Okay. So there's where the classical step comes in and says,
yes.
You just cost too much. Let's not do that. Let's revert back. Okay.
Exactly.
Okay.
And different classical optimizer will do it differently. Yes, but it's guaranteed to work that way. Right. That's a very good question. And now with the ansatz, we come to the last piece of.
Sorry, now I want to pursue that one more step. Okay, so any solution which is an eigenstate, if you like, of the original any eigenstate of the original Hamiltonian is a solution, but not the true solution. It's an invalid solution because it costs more than the best solution. But still, if you land on it, and then you get kicked out. How does the classical optimizer say, well, wait a second, you had a good solution. How does it know it's not the optimum solution?
Oh, because let's remind again. So any solution you get will be either true, false, or invalid. So most cases you have a false or invalid solution. When you have an invalid solution, you have this binary constraints. The constraints are kicking. It'll make your cost really high because lambda and all those constraints.
No, I'm interested. What I'm asking about now is the false. I have a false.
Right.
I hit on a false.
The false will not give you a low enough profit of the distance. So the distance will be higher than what you get when you have a true solution. So if the optimizer is smart and able to search everything, it will find later that it's not the optimal one. So it will reject that solution. all
So
the parameters.
Okay, so what I hear, I think I'm picking up on this, that the optimizer must somehow explore phase space sufficiently to detect that although you found a false solution which satisfies the Hamiltonian eigenvalue problem, it's somehow not the optimum
Right.
solution somehow. So here's where the dependence on your optimizer becomes critical, right? I mean, you have to have somehow.
You also yes.
Okay.
You also need to have compatible mixers, and allow you to explore everything that is possible, right? So it's a combination of the two. Yes, I would say dependent on optimizer is really critical.
Question following up on that, but if you have a lot of local minima, depending on how deep they are, you may never get out.
Yeah, it's very hard, especially as the problem size increases. Yes. But the thing is that so you have very few parameters, and if your parameters can fully parameterize your search space, and this is possible, yes. But that might require you to have more layers in a harder TSP problem. I don't know whether I fully answered the question.
Okay, so you're limited by having chosen P layers.
Right, but if P equals 1 doesn't work, you can always go to higher P's, and the performance is guaranteed because it's basically inspired by the quantum annealing as P goes to infinity, and as P increases, you basically you can control the precision, so your final result is within some proven threshold of the optimal solution. Yeah, this is a heuristic approach. So you're not guaranteed 100% of time to get the solution every time you run it, right? So there's that, yes.
Okay, thank you.
Yeah, maybe it'll become clear when I talk about the measurement and the results. So for the measurements, in the optimization loop, we have these classical optimizers, and so here, so I have I've used several optimizers, but here I will just focus on the constraint optimization by linear approximation, or the COBILA, the very popular one. And we run each QAOA instance multiple times, or sometimes I call it batches, typically in the order of 5 to 10 batches. And so here is a plot of the cost expectation after each iteration loop for 3 different batches of the same TSP problem. As you can see, you have those up and downs. So that's a battle between the problem and the mixer ansatz, and you have eventually some kind of convergence in the end. And depend on your parameter determined by the optimizer, each time is following a different random seed. So you might end up different place here, and we usually pick the one with the lowest cost expectation. And if you look at each of those a curve and draw the parameters as a function of iterations, you will have something like this, okay, which is also this is also very good to see here. And for one layer, you will just have 2 parameters. So that's what we draw here. And in the result part, we will only present the best result based on the cost function expectations, as you can see here, and also the accuracy of the solution. And we use only the simplified encoding, which means we use 1 less qubit for each city. And several configurations that so I have considered. So the red part is basically on quantum computer, and the green part is on classical computer. And so the case 1, you can have the Hadamard initialization together with the X mixers, and using the Euro problem Hamiltonian. with the basically what I mean is with the penalty, right? So that's one way to do this, and so this is the original QAOA approach. The heavy duty in this method is that your optimizer or your cost evaluation function needs to determine the parameter. So all the weight lies on the classic computer. So in that sense, and recently the case 2, you can have a single valid state and apply the row swap mixer. And because the row swap mixer will have the constraint built in, because you always swap 2 cities. So when you start with a valid permutation, you always swap the corresponding swap the 2 elements in the permutation, you will never get an invalid solution, right? So that's very nice. So you don't need to put your cost penalty. So you don't need to have the penalty term in your Hamiltonian. So your Hamiltonian is slightly simplified. And the classic optimizer also likes it because you have only a single state and you have a constrained mixer, and you don't have much measurements in the end. And it's very light weighted for optimizer, but the heavy duty is on the row swap. I'll show you in the actual result. This term will become very, very long on the quantum circuit. But the performance is very good for case 2. And third, you could have a W state, as I mentioned before. So instead of binary superposition, you have one hot superposition, reducing the state space, and you have the XY mixer to conserve the swap. And then we use the normal Hamiltonian with the penalty. So in this approach, so we spread the burden to initialization and problem Hamiltonian. So it's very balanced in this case. And the fourth category, so you could also start with a valid superposition. So instead of starting with W state, you can have only the valid superposition, and the same thing follows for case 3. So this would be nice because if you only consider valid superposition, so you have much less states to consider. But this part itself on a quantum computer is not very straightforward, and it's in general very hard on the real quantum computer. So the heavy duty is really on the initialization part. So here I just the many other categories you can think of, and you could apply different mixers at different layers. So the structure is very, very broad. It's like working with the neural network in a sense. And so these are some preliminary results based on the first 3 cases. So you can have a Hadamard plus the X mixer. So let me explain this graph here. So you have 2 rows here. So the first row represents the study of 3-city traveling salesman, which require you to have 4 qubits. And so these 2 plots is showing you the final result, the histogram, after you optimize your ansatz. So with the optimized parameter, and you run your Hamiltonian, and this is the histogram that you get, which is the probability distribution of different decision variables. And as you can see, the decision variables can be grouped into true, false, and invalid. And in this graph, you can see the true solution dominate the probability distribution in the end. And the minimum distance for this particular graph is 217. And the true solution, basically, whether you go from 0, 1, 2 or 0 to 1, right, will both give you the same distance. So it's very common that you have 2 different routes that give you the same minimum distance. And the invalid solution are also listed here. And it was very important to notice that for a 3-city traveling salesman, there will not be any false solutions, because any invalid solution will be a true solution, because any permutations you go will solve your traveling salesman. And so, and the right graph basically map, so left graph only show you the top 20 counts, but the right graph show you all the counts. Basically, you convert the decision variable into decimal places and plot the probability distribution. And you can see their relative location when it's on decimal place. And the brute force result is highlighted with the dashed line. And you can see the true solution lined up with the brute force solution. And thing value usually is yeah, so those two are reflected here. You have a very small space to consider. So actually you have 16 possible outcome, right? So that's for the 3 cities. In the case of 4 cities, the problem is much harder. You have 512 possible states to consider. And as you can see, the this headmap plus X configuration doesn't quite work, at least for owning 1 layer. So the solution space, your top 20 solutions are dominated by the invalid solutions. And if you plot every solution on the right, you will see that the true solution is really hiding inside the dominant invalid solution, along with the false solutions. So this is only for 1 layer. And for case 2, you have the single valid state plus the row swap mixer. So for 3 cities, as you can see, because of the nature of the row swap, you start with the valid solution and you try to swap it. And for 3 cities, every valid solution is a true solution. So that means you have very simple results like this. That is just guaranteed from the start, basically, right? But it's still good to see that you are able to, rotate to the other solutions in your solution space. And I have to say, this is on a quantum simulator. All the results on a quantum simulator. On a real quantum computer, this will not happen. It will not be this clean, because you have a lot of noise that's coming into play. And for a 4 city TSP problem, you can see that you will still have a dominant solution being the true solution. And so those 2 solutions here are false solution, but it's very small in comparison, and you will still not have any invalid solution. And the probability distribution is also very nicely demonstrated here. And of course, I always start with the valid solution that is not a true solution. Otherwise, there's no point of solving the problem, right? Because you already know the solution at hand before. So, but you can see the row swap mixer is able to rotate your solution to the true solution. And I have also done a test for 5 cities and 6 cities. For 5 cities, it also can do the trick. For 6 cities, at 1 layer, it start to having problems. But I will not show the result here today. And for the case 3, we have a W initialization state and the XY mixer. So remember, this is a more balanced approach. And for the 3 cities, we can have this very nice result where the 2 solution is actually so this is very similar to what you get for row swap, except for the fact that the 2 solutions are more evenly spread. And for the 4 cities, you kind of also get the dominant solution as being the true solution, but you have the probability graph will not be as clean as a row swap. You have a lot of false solution and invalid solution in the mix, right? And this will be the full histogram of the solution. But this can be advantageous. Sometimes if you only look for the dominant solution, you do not care about the probability, and that's what mostly when you want to make a decision is about. So this method can be handy. And so here are cross comparison all three methods as the number of layer increases. So on the left, you see the result for 3 cities. On the right, you see the result for 4 cities. For 3 cities, so you have 3 categories: the case 1, case 2, and case. So this will be case 1, case 2, and case 3. And for the Hadamard plus X, as the number of layer increases, the invalid solution will become more and more dominant. And but for the W plus XY, it's gradually approaching 100% as number layer increases. And for the row swap, it's always 100%. It's really good in this regard. And when you have 4 cities, as you already see, the pool performance of the Hadamard plus X combination, and also as the layer increases, I noticed the W plus XY will have a decreasing trend for the true solution, which is, and the row swap still is very good. But one thing to mention here, this probability column is of different color is actually combining the probability of the same color. So normally you have a lot of 4 solutions, so especially in the W plus XY, and only 2 true solutions. So although on the graph you see the dominant invalid solutions, but the true solution is still the dominant one when you plot like this. Okay, so there is that. And so this layers, although this is very preliminary results, it may suggest to me that variational algorithm might not be very reliable with more depth. So there are many factors that can influence. So with increasing layers, we must consider how we want to make changes to the mixers and others. And so accuracy is only one aspect of the algorithm, right? There's also this cost or performance versus number layers. So on the left, you see the expectation cost as the number layer increases for each category that we studied. And for the row swap, it stays very flat. That is, so when your true solution is almost 100%, so that means your expectation cost is very close to the true cost, right? So that's just a way to reflect that. And then as number of layer increase, there's a general trend of decreasing in the expectation cost, which is but it's not seen here for this case, but it's very general. And but the time cost is another different story, because as I said, the row swap put all the resources on the row swap mixer. So the row swap mixer is very heavy. So the time complexity is not so good for row swap. So this shows you the runtime that I run on my desktop, which is the very old desktop. It still does show you the trend as the number of layer increases and as the number of city increases, how the runtime increases. And for row swap, in particular, you will need like around 5 to 10 minutes for just 1 layer for city. And for 5 cities, this will quickly become approaching an hour to run. Okay, so that's that disadvantage for row swap. And so it turns out that the more balanced approach is actually the fastest to perform. And this shows you the number of gates that you need. So on the left, you have this single qubit gate and double qubit gate. On the real quantum computer, the double qubit error is really the main source for the gate error. And for row swap, as you can see, this number is incredibly big in comparison with the 2 other approach. Okay, so I'm approaching the end of my talk. So, how we go forward with this approach? So, one key idea is to explore more mixers, but we will also consider both the runtime complexity and the performance. If you combine those two into account, the row swap might not always be the best option, especially in the scenario that we are only interested in a dominant solution, right? So when we solve a traveling salesman, we do not care about the probability for a dominant solution. We want to know if the dominant solution is the true solution. And another aspect of row swap that is not very appealing to me is that it's not taking advantage of the quantum superposition efficiently by starting with a single state, right? And then there's many different structures that I propose on the basis of using XY swappers. So you could have, so this is what we have now, using the same parameter for all the XY, but you could have different parameter for different blocks of XY. And you could also have a cyclic encoding instead of a linear encoding. So the many options to explore. And there are many studies looking at the different mixer variants. One particular work look at a Grover mixer, which is taking advantage of a Grover algorithm and the mixer. And another very recent study, just last year, is about using boosters in between layers to further boost your result. So that's something that we are also very interested in trying. And lastly, we have the summary. So we solved the traveling salesman problem using QAOA approach on quantum simulators in the case of 3 and 4 cities. So the study of 5 cities and 6 cities are underway. We present a multiple choice of initial and the mixer to solve the TSP. And we evaluate performance based on accuracy as well as time resources. So I think the key idea is about shifting the hard and soft constraints into various components of QAOA. So the hard constraint here will be the causality that your solution has to obey, whether it's a valid or invalid permutation. And soft constraint is that whether your distance is minimized, right? So you want to shift those constraints into various components of QAOA, especially the initial states, mixer, problem Hamiltonian, and optimizers, which is one thing that we haven't studied too much. So, and ask the question is a balanced algorithm better than a heavy-headed one, as you can see in the row swap. And a few things that we will look forward to are here. Yeah, thank you very much.
Thank you, Wenyang, for the great talk. I think the traveling salesman problem was first formulated something like 1930s, which would make it older than computer science itself. So it's very interesting to see how such a long-standing computational problem can be approached in new ways with quantum computing.
Right.
Anyways, with your permission, I'd like to now open the floor to any questions the audience may have. We generally just raise our questions organically in these seminars, but if anyone ends up having trouble finding an opening in conversation to ask their question, you can also raise your hand on Zoom or write your question in the chat, and I'll help make sure we get to it.
Okay.
So I have a question. In QAOA, you have two sets of parameters, one for your model Hamiltonian and one for your mixer Hamiltonian.
Right.
And are they an equal number of parameters typically for the model and the mixer? Okay.
Yes.
Equal number. Is it understood that they should be equally treated as parameters to be optimized? I mean, for example,
that's a very good question. So in the past, most studies on this have been using the same parameters. But people have now loosened the constraints for those ansatz. So that is why in a new formulation, so I kind of propose you have 2 parameters for each layer for the mixer, but 1 parameter for the problem Hamiltonian. So now people have really open up the constraints, I think. Yes.
Yeah, because I have some experience with classical Hamiltonian problems where I actually have too many parameters to search on. And
Right.
this leads to instabilities in search procedures. You can imagine an overly parameterized problem, I guess is the way I would say it. So that the solution becomes, in some sense, ill-defined in the problem, in the variational search procedure.
Right.
I try to remember a concrete example I could give you, but it doesn't come to mind offhand. But anyway, so I worry that there might be too many parameters.
Oh, I see.
More than are necessary to solve the problem, if you like.
Okay.
Oh, you would have hidden symmetries, right?
Yeah, that's right. That's right. This could be part of the story. Yeah.
Right. But for the QAOA, you just have very few parameters. Like in those two graphs I showed here, you only have 2 parameters for each graph. And as the number city increases, you still use the same 2 parameter, and it seems to work very well. And even for 5 cities and for 6 cities. So I think for QAOA, it's a very different story. You have very few parameters at the first layer, and your parameter only increases as your layer increases, not as your problem size increases.
Okay.
But of course, as I mentioned, that the approach is not really opened up for more varieties, and you can have more parameters than you want. Yes.
So, but perhaps to put it another way, by changing the number of layers, you can change how many if your problem needs more parameters, adding more layers gives you more parameters. But if it doesn't, then you just have fewer layers.
Yes.
I guess another question I would have is, okay, so there has been success in modeling the problem through an Ising Hamiltonian. Are there other candidate Hamiltonians out there that people have introduced as possible Hamiltonians to represent this actual classical problem? I think the point I'm making is you have a classical problem, you're modeling it as a quantum problem, but a classical problem in principle has an infinite number of quantum problems for which it is the limit. And so the question is Ising the only game in town, so to speak, or?
For the traveling salesman problem itself, I have only seen Ising formulation, but for a general classical problem, you can have many different formulation of Hamiltonian, right? So you have, yes. So in general, it's not. But for TSP, so far I have seen our Ising formulations.
Okay. I guess maybe if the opportunity arises to ask yet one more question. So you've done this initial study with simulations rather than actual quantum computers, but simulations also allow you to introduce noise into the simulations itself.
Right.
Any idea what would happen if you did introduce noise into these simulations?
So for that, you will build your noisy model, so you have a controlled noise, and as you can imagine, as if you set the noise threshold to match that of the current quantum backends, the performance will not be great. I would even think row swap will have difficulty to run on a noise controlled simulator. But as you lower the noise low enough, the simulation will gradually approach what you have with a perfect sampling simulation you see here. But that technology is still underdeveloped in real life, right?
In that regard, actually, in a previous talk, we saw how in certain scenarios you can even make quantum noise work for you in your algorithms. Is it possible that, or do you know if anyone's has considered the idea of for instance, one of these hybrid approaches, so like this one, using the quantum noise just to help with the sort of, as it was noted before, if you get stuck in a local minimum, helping the noise just helping keep you bumping around a bit to make sure that you don't get too narrowly focused in the I don't know, configuration space.
Yeah, I think that's part of related to the idea of quantum annealing in the original method that is proposed almost 50 years ago. So basically, you start with like a hot temperature, so your solution bump around as the temperature decreases, and you will gradually approach the true minimum, right? And the bumping really helps you that. But for the QAOA, I haven't seen much study on TSP. The QAOA approach is mostly used on max cut problem, not so much on traveling salesman using real quantum computers. Yeah.
Well, if we have no further questions, I'd like to thank Wenyang again for the great presentation, and thank everyone for coming and joining us for his talk. Will be there are plans for the next speaker for next month, details of which will be sent out once things have been confirmed a little bit more. But otherwise, thanks again, and I wish all of you to have a excellent day and excellent week.
Okay, thank you.
Thanks, Wenyang.
Thank you.